Now see here equipotential surfaces here. So an equipotential surface is a surface with a constant value of potential at all points on the surface. So if you have taken a surface where potential at every point remains same, that is known as equipotential surface. So suppose if you have got a point charge over here, a q, and we know it, V is equal to q upon 4 pi epsilon naught r. This is the potential at any point at a distance r. So if you take this distance r, at this point potential is this much. So if you draw a sphere here like this, you will find at every point on this surface potential remains same because r is here same. So this surface is known as equipotential surface. But as the distance increases, potential reduces. So if you can take this one, another we can take like this. So there are the spheres, concentric spheres here, which are acting as here equipotential surfaces here. So equipotential surface for the point charge can be drawn in this way. Now see here, first I have taken here electric field, that is a uniform electric field along the x axis, and there are the equipotential surfaces normal to this x axis here. These mean the planes parallel to yz planes or parallel to yz are acting as equipotential surfaces. So for uniform electric field, first equipotential surface is this, second equipotential surface is this. And this is also the equipotential surface for an electric dipole. There is a minus and plus here. So equipotential surface you can draw for this electric dipole. So we have seen equipotential surfaces for a point charge, that is a concentric spheres, spherical surfaces, and for uniform electric field, that is the plane perpendicular to the electric field here, and also we have taken here the equipotential surfaces for an electric dipole. Now see here, in equipotential surfaces we have seen here the potential remains same at every point. It means we can write here potential difference Vb minus Va is equal to 0 in equipotential surfaces because Vb is equal to Va. Now if you have got equipotential surface and charge is moved from one point to another, suppose there is an equipotential surface here like this, and here electric field is to this side. Now a charge q is moved, suppose from here to here by a distance. This charge is moved in the equipotential surfaces by suppose a distance dr. In this case we can write work done is equal to here work done to move from A to B is equal to WA to B is equal to here Vb minus Va into Q. But Vb minus Va is equal to, actually they are equal because that is the equipotential surface, so this will be 0. So work done is 0. So when the charge is moved from one point to another in the equipotential surfaces, work done is 0. So we have done work done in moving the charge through a small distance in equipotential surface is 0, and that can be written WA to B is equal to here Vb minus Va into Q, that is equal to 0. And also we can write here vector E dot vector dr is equal to 0. Electric field and dr is the distance moved in the equipotential surface and E is electric field. So we can write here E dr cos theta is equal to 0. So here E is not 0, dr is also not 0, it means cos theta is 0 here. So cos theta is 0, that means theta is equal to 90 degree. That we can say here E is perpendicular to dr. It means electric field is perpendicular to the equipotential surface at any point. So we can also show this thing, or this one electric field is perpendicular to the equipotential surface at any point by using this concept.